Hello, welcome to the video of session 4 of module 2 fast Fourier transform algorithm of the subject digital signal processing prescribed for 5th semester electronics and communication engineering students. Now let us see the learning objectives of this session. Here, we will be beginning with a discrete Fourier transforms concept. Then, we will be considering computational complexity in direct computation methods for finding DFT. Then, we will be discussing need for efficient computation of the DFT. Afterwards, we will be considering classifications of the different algorithms. And we will be concluding the session with considering the concept of radix 2 FFT algorithms. First, let us take discrete Fourier transforms. Before considering actually this discrete Fourier transform, first let us see what is our digital signal processing. So, as we are knowing, the signals from the natural sources are most of the cases we can consider it as in all the cases it is analog in nature, that is continuous in nature. And for doing the signal processing operation in digital domain, that is in digital signal processor for processing or manipulating or analyzing purpose, we have to have the signal which is in digital domain. So what we need to do, the signal which is continuous in nature from the sources has to be converted into digital signal. Then we have to perform the operation. Then we will be obtaining the output which is again in digital form, but we require that in analog form again. So we have to consider that back to the analog. So in doing this process, we have to consider the signals. And we will be having the signals which is most of the cases which is in time domain. But analysis purpose and for manipulation purpose, it is easier for us to perform which is in frequency domain. So what we have to do is we have to convert or we have to transform from time domain to frequency domain. And from the basic mathematics, all of us knowing that Fourier transforms converts from time domain to frequency domain. But observe that Fourier transforms which converts the time domain which is in discrete form that gets converted or transformed to frequency domain, but that frequency domain signal is in continuous form. But that is not required for us because that cannot be processed using our digital signal processor. So what we need to have? We have to have the frequency samples. So now let us come to our discrete Fourier transforms. To get the samples of frequency domain signal, we have to apply the discrete Fourier transforms. So sampling of frequency signal will be our discrete Fourier transforms, that is x of k. And one more thing, to reconstruct the discrete time signal which has converted into frequency domain samples is nothing but inverse discrete Fourier transforms, that is x of n. Now let us have this discrete Fourier transforms. As the basic knowledge, it converts a time domain signal to frequency domain discrete sequence, and it is a powerful computational tool that performs the analysis of, or we can say frequency analysis of discrete time signal. And this can be used to perform the linear filtering, correlation analysis, spectral analysis, and all those basic signal processing operations. Now, let us have the computational complexity in finding discrete Fourier transforms using direct computation method. So, first let us consider the equation for discrete Fourier transforms. For finding endpoint DFT of the sequence x of n, we have the equation which is x of k is equal to summation n varying from 0 to n minus 1 x of n into omega n raised to the power of kn. Here the value of k, that is x of k, here this DFT is varying from 0 to n minus 1, that is there are n samples in x of k. So if we expand this equation, what we obtain? x of k is equal to x of 0 into omega n raised to the power of 0 plus x of 1 into omega n raised to the power of k plus x of 2 into omega n raised to the power of 2k etc. up to plus x of n minus k into omega n raised to the power of n minus 1 into k. Observe here, this represent first complex multiplication, and this one represents the second complex multiplication. This is third one. Similarly, this one represents the last complex multiplication, that is nth complex multiplication. Similarly, you can observe here, this is the first complex addition, this is the second complex addition. Similarly, this is the last one, that is n minus 1th complex addition. Why we are considering this as complex multiplication and complex additions are, we are multiplying two complex numbers. Similarly, multiplication of two complex numbers leads to add two complex numbers again. So this is complex addition. So here we can observe there are n minus 1 complex additions involved for finding one value of k, and there are n complex multiplication for one value of k. So, number of complex multiplication required for calculating x of k for the value of k varying from 0 to n minus 1. That is, for n value of k, there are n into n, that is n square complex multiplications. Similarly, number of complex additions required for calculating the DFT x of k for value of k varying from 0 to n minus r n minus 1 into n, that is n square minus n complex additions. So, just consider one example to evaluate 1024 point DFT. That means value of capital N is 1024. Complex multiplications involved are n square, that is 1024 square, that is approximately equal to 1 million complex multiplications. And complex additions involved are n square minus n, that is 1024 square minus 1024. That gives approximately again 1 million complex additions. So now let's have, what's the need for having efficient computation of the DFT? Okay, let us assume our digital signal processor executes one complex multiplication in 1 microsecond, and also let us assume one complex addition, it can be executed in 1 microseconds. Okay, so if we consider the same n is equal to 102 point DFT, finding this, so time required for computing n is equal to 1024 point DFT will be, see, time is equal to total number of complex multiplications into time for one multiplication plus total number of complex additions into time for one addition. So, if we substitute these values, which is equal to 1 million into 1 microsecond plus 1 million into 1 microsecond, that gives us 1 plus 1 seconds, that is equal to 2 seconds. So, 2 seconds is not a desired thing for us, because need for having DSP, that is digital signal processor, is to have the faster operation. 2 seconds is much here, so we cannot use this for real time processing. So we need to have the computational method which gives us the DFT in a faster way. So now let us have the complete complexity involved in finding DFT in direct computation method. Again, let us consider endpoint DFT of the sequence x of n, which is x of k, which is equal to summation n varying from 0 to n minus 1, x of n into omega n raised to the power of kn for the value of k varying from 0 to n minus 1, where our Wn is called twiddle factor or phase factor, which is given by e raised to the power of minus j2 pi by n. So, if we consider our time domain sequence x of n as well as the twiddle factors are complex valued. When can we say a number or a signal is a complex valued? Where our sample is having both imaginary as well as real part. So here what we are doing is we are considering both the input signal as well as the twiddle factors as complex valued. So now what we have to have our x of n which is as a complex valued as well as twiddle factor as a complex valued. So x of n can be written as x r of n plus j times xi of n. Here you can observe here x r of n represents real part of x of n. So, and xi of n represents imaginary part of x of n. Similarly, our twiddle factor omega n raised power of kn is equal to wrn raised power of kn plus win raised power of kn. So, this wrn raised power of kn represents real part of twiddle factor, and this win raised power of kn represents imaginary part of twiddle factor. Okay, that constitute our Wn raised power of Kn. So now let us do one thing. Let us expand this x of k equation by substituting x of n and Wn raised power of Kn as complex value. So this is how we can do. Our x of k is equal to summation n varying from 0 to n minus 1 xr of n plus j times xi of n. This is multiplied by wrn of kn plus win raised to the power of kn. Okay. Now if we simplify this, that means if we expand and simplify, what we obtain is, see, summation n varying from 0 to n minus 1 xr of n into wrn raised to the power of kn minus xi of n into win raised to the power of kn plus j times xr of n into win raised to the power of kn plus xi of n into wrn raised to the power of kn. So, conversion of one complex multiplication. Which is one complex multiplication? That is multiplication of two complex number. As we considered our x of n as well as the twiddle factor wn as complex number, as we are having that x of n into wn raised power of kn, so that complex multiplication, that one complex multiplication, now it is converted into this term. Okay, so now that one we are considering conversion of one complex multiplication into this. You can observe this within the brackets. Okay, within this flower bracket, the things we have considered here, and observe, see that one complex multiplication is converted now into four real multiplications. See, xr of n into wrn raised to the power of kn, that is one real multiplication. xi of n into win raised to the power of kn, this is the second real multiplication. xr of n into win raised to the power of kn, this is the third one, and the last is xi of n into wrn raised to the power of kn. So there are four real multiplications. Okay. Similarly, two real additions. We can observe here xr of n into wrn raised to the power of kn minus xi of n into win raised to the power of kn. So this addition, my negative means subtraction means addition of negative values. So we can consider both addition as well as subtraction as addition itself. So this is the one real addition. Why it is real addition means this term is free of j term. Similarly, here also we can observe within this bracket which is free of j term. So we are considering this addition again as real addition. This is the second real addition. So what happens here? One complex multiplication is converted into four real multiplications and two real additions. This is for one value of k. So one complex multiplication is converted to four real multiplication and two real additions. But for each value of k, there are n complex multiplications. So the n complex multiplications are converted into 4 into n, that is 4n real multiplication and 2n real additions. So for complete DFT, there are n into n complex multiplications. So those n into n complex multiplications are converted to 4n square real multiplications and 2n square real additions. So now let's have a general complex addition. So now consider conversion of one complex addition. So here, why it is one complex addition is which involves addition of two complex numbers. So a plus jb represents one complex number. Similarly, c plus jd represents another complex number. So this represents, left hand side represents the one addition complex, sorry, one complex addition. Okay. So there are two complex number here that gets. So if we simplify this, that means if we separate the real part as well as imaginary part, we obtain the right hand side. So two complex numbers are converted into single complex number. That's one complex number. Okay. One complex multiplication now is converted to two real additions. Hope you understood this. So one complex addition is converted to two real additions. One complex addition involves two complex number, but this simplified form represents or having two real additions with one complex number. Okay, so one complex addition is converted to two real additions. But for each value of k, there are n minus 1 complex additions as we considered before. So n minus 1 complex additions are converted into 2 times n minus 1. That is 2 into n minus 1 real additions. So for complete DFT, there are n into n complex additions. So our n into n complex additions are converted into 2 times n minus 1 into n. That is 2n square minus 2n real additions. So total real additions in computation of DFTs are 2n square plus 2n square minus 2n. That is 4n square minus 2n, which is equal to n into 4n minus 2 real additions. Total real multiplications in computation of DFT is 4 into n square. So, as we know from the definition of DFT, W n raised power of kn, that is twiddle factor, is equal to e raised power of minus j 2 pi kn by n. By Euler's identity, that is exponential raised to the power of minus j theta, that is e power minus j theta, is equal to cos theta minus j sin theta. So if we substitute this in this, so what we obtain for Wn raised power of kn is equal to cos of 2 pi kn by n minus j sin of 2 pi kn by n. So here the term cos of 2 pi kn by n represents real part of twiddle factor, and Wn raised power of kn is equal to minus Win raised power of kn is equal to minus j sin 2 pi kn by n represents imaginary part of the twiddle factor. So now let us consider two trigonometric values are executed for every value of Wn raised power of kn. So for n varying from 0 to n minus 1, Wn raised power of kn takes n different values. Okay, and for the value of k varying from 0 to n minus 1, our twiddle factor, that is Wn raised power of kn, takes n different values. Okay, for simultaneous variation of both k and n, our twiddle factor takes n into n, that is n square different values. Okay, so total number of trigonometric values evaluated will be 2 times n into n, that is 2n square. So now let's have computational complexity in direct computation of DFT. So summarizing this one, so let's have the operations involved as well as number of computations which representing. Okay, first one is complex multiplications, that's n square. So there are n square complex multiplication for finding n point DFT. Similarly, complex additions are n square minus n. So n square minus n complex additions. Similarly, 4n square real multiplications. 4n square minus 2n real additions. And there are 2n square trigonometric functions involved in direct computation of DFT, that is using expansion kind of method. Okay, so Along with this computational complexity, it requires a number of indexing as well as addressing operations for finding DFT using direct computation method. So, before proceeding to the further session, let us consider some of the properties of twiddle factor. Okay, twiddle factor is also called phase factor. So, our endpoint TFT x of k is represented by summation n varying from 0 to n minus 1 x of n into w n raised power of kn, where our value of k varying from 0 to n minus 1. Okay, here our wn raised power of kn, that is twiddle factor, is nothing but wn, which is equal to e power minus j 2 pi by n. This twiddle factor or the phase factor are having some of the properties. One of that is symmetry property. According to the symmetry property of our twiddle factor, wn raised power of k plus n by 2 is equal to minus wn raised power of k. And one more property is periodicity property. That according to periodicity property, our twiddle factor Wn raised power of k plus n will be equal to Wn raised power of k. So now let us have what is the need for efficient and fast method to compute DFT. As we know from the basic that DFT is a widely used mathematical tool in our DSP algorithm. Why we are calling DFT as a mathematical tool is our discrete Fourier transforms convert the time domain signal into frequency domain discrete samples. So it is acting as a mathematical tool. And this discrete Fourier transforms can be used for performing linear filtering operation, correlation analysis, spectrum analysis, and other similar kinds of operations. And our direct computation of our DFT involves large number of computations. And many algorithms are available for finding DFT. Okay, each algorithms have their own merits as well as demerits, but we have to choose the algorithm which fits for our purpose. So now let's have the classifications of the algorithms for finding or computing DFT. So our computation of DFT is broadly classified into two methods. That is two approaches. Using two approaches, we can classify. One is divide and conquer approach and DFT as a linear filtering. Okay, so here what happens, let us consider this divide and conquer approach later. First we consider DFT as a linear filtering. So here if we want to find DFT of certain points, that means if we for example for endpoint DFT, if suppose value of n is 8, so if for finding 8-point DFT, if we require only 6th point value, that means x of 6. So what happens, we have to find particular point value. In that case, finding 8-point DFT for all the values is waste of time. That consumes more machine cycle. So in such situations, we will be going for DFT as a linear filtering. Okay. Here there are two methods in case of DFT as a linear filtering. So one is chipset transform algorithm and other is Godsell algorithm. So, but for this particular session, we are not concentrating on this DFT as a linear filtering operation. So now we are focusing on divide and conquer approach. Okay. So computation of DFT, if we classify, we obtain two. In that first part, divide and conquer approach, again it is converted. It is classified as three different algorithms. Okay, three different kinds we can say. So in that divide and conquer means we are, if we suppose if we are taking endpoint TFT, we are dividing it, and that means we are decimating, we are splitting like that. Okay, so there are three algorithms, main algorithms in and comes under divide and conquer approach. In that first one is radix to FFT algorithms, second one is radix for FFT algorithms. Third one is split radix algorithms. So for fifth semester electronic students, they have mentioned only two algorithms which comes under divide and conquer approach and radix to FFT, in that DIT as well as DIF FFT algorithm. So our radix to FFT algorithms are again classified into decimation in time FFT algorithms and decimation in frequency FFT algorithms. So this is how we can classify the computation of DFT. So as we considered here, FFT, that is radix 2 FFT algorithms, radix 4 FFT algorithm, split radix algorithms. Here, these comes under divide and conquer approach. So in that radix 2 FFT algorithm, we are considering DIT FFT as well as DIF FFT algorithm. So the focus, what we need to focus is on FFT algorithms. FFT is nothing but fast Fourier transforms. So now let us have this fast Fourier transforms. So this fast Fourier transforms algorithms has been published by Cooley and Tukey for computation of DFT that is applicable when n is a composite number. That means whenever in the real-time signal processing, whenever the value of n is a composite number which is larger in size, then we need to have the computation of DFT which is in divided form. So that algorithm is published or considered by Cooley and Tukey, and they published they developed this fast Fourier transforms. Cooley and Tukey developed our fast Fourier transforms in the year 1965. This particular FFT, that fast Fourier transform algorithm, is an efficient algorithm which is used to compute discrete Fourier transforms with less number of computations. And this FFT algorithm requires a very small storage memory storage requirement. Okay, and due to efficiency of our fast Fourier transforms, this fast Fourier transform can be used to perform spectral analysis, convolution, correlation, linear filtering operations, filter simulations, pattern recognitions, and many other applications. And we can we can highlight one point is our real-time implementation of DFT is possible only because of the FFT algorithm. So this is the speciality of our FFT algorithm that makes us to have our DFT implementation in real time. So if we consider radix 2 FFT algorithm, there are two FFT algorithms, radix 2 FFT algorithm available. One is radix 2 decimation in time FFT algorithm, that is DIT FFT algorithm, and radix 2 decimation in radix 2 decimation in frequency FFT, that is DIT FFT algorithm. So we will going to consider this radix 2 FFT algorithms, that is DIT FFT algorithm as well as DIF FFT algorithm in the upcoming sessions. Okay. So summarizing whatever the things we have learned in this session are discrete Fourier transforms. Then we considered computational complexity in finding direct computation and total computation complexity we considered. Then we look at what are the needs of having efficient computations for finding DFT. Then we considered classifications of algorithms available for computing DFT. Then we concluded this session with radix to FFT algorithm. Okay, these are the references which we considered. Book by Prokis and Monolakis, that is Digital Signal Processing Principles, Algorithms and Applications. The next second book we considered is book by Li Tan and Jin Jiang, from the book Digital Signal Processing Fundamentals and Applications, and the book by Uday Kumar, Mr. Uday Kumar S. The book is Digital Signal Processing. Hope you understood the concept which we tried to explain in this session on discrete Fourier transforms. Okay, for further material which you people can refer to is we have been the links here. You can refer to the video by accessing these links. Okay, in this you can access using the link this session. Okay, then for questionnaire and multiple choice questions you can access through this particular link, and for notes you can check with this links. Okay, uh, thank you all. This is the LMS team. Please